Hello everyone. Today we discuss combination of continuous function. In this session, we consider function f and g, and they are defined from some subset A to a set of all real numbers. Suppose that the function f and g are continuous. At some point C in the subset A and B is a constant. Then we have the following. The function f plus g, the function f minus g, the function f multiplied with g, the function b times f, they are all continuous as C. So the algebraic combination of these two functions f and g are all continuous as C if f and g are continuous as C. Furthermore, if g of c is different from 0, then the rational function, the quotient f of x divided by g of x is also continuous as c. This theorem basically is about the compatibility of continuities and algebraic operations. In a way, this is similar to the compatibility of the limit concept with algebraic operation. And this is not surprising because continuity is defined using the limit concept. Now we have a theorem which say that we can replace the point C here by the set A. Again, continuity is a local condition. If certain property is true at one point and it's true at any point in a set, then we say that that property is true for the set. Now, the next goal is to establish continuity for fundamental function. The first is a polynomial function. We consider the polynomial p of x equal to an x to the n plus an minus 1 x to the n minus 1 plus dot 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 plus a1x plus a0. We observe that x to the n here, this is just the multiplication of n copies of x. Each function x is continuous by the previous section. Therefore, using the theorem we just established here repeatedly, we show that the product of n copies of continuous functions is continuous. Consequently, an xn is also continuous because it is just the multiplication of xn by a constant. Now, the polynomial p of x, as we see here, is just a combination of continuous function. So it is continuous on the set of real numbers by the theorem above. So to summarize, in order to show that the polynomial function is continuous, we show that each term in the definition of this function is continuous and the function is just an algebraic combination of these continuous terms. Therefore, the theorem above is applicable and implies that the polynomial is a continuous function. Now we consider a rational function f of x equal to p of x divided by qx for pq are polynomials. By an argument similar to above, we can show that f of x here is continuous at every real number for which q is different from 0. That is, every real number for which the function is defined. So basically, for the rational function, we use part B of the theorem repeatedly in order to use part B of this theorem. We need to verify the condition that the denominator is different from 0. That's why we need that assumption that the cube x is not equal to 0. Now, it is stated that sine x and cosine x are also continuous on the set of real numbers. The proof for this function is a little bit involved and it goes beyond the scope of this class, so we're not discussing it here. Now we have theorem about continuity and absolute value. Let's consider the absolute value function, absolute value of f evaluated at any number x e equal to the absolute value of f of x. If f, the theorem says that if the function f is continuous as c, then the absolute value function, capital absolute value of f is also continuous as c. Similarly, we can replace c here by the subset A. I'm gonna give a proof of this theorem to illustrate how we utilize all the materials we learn in order to prove this statement. F is continuously is equivalent to limit statement. So this is what we learned from section 5.1. We want to show that the similar equation is true for the absolute value function. And this is equivalent to limit equation. The limit when x approaching c, absolute value of f of x equal to absolute value of f of c. In order to show that, we observe that the absolute value of f of x minus the absolute value of f of c is smaller than or equal to the absolute value of f of x minus the absolute value minus f of c in absolute value by the triangle inequality. Similarly, we can reverse this equation. So the absolute value of f of c minus absolute value of f of x is smaller than equal the absolute value of fc minus fx. Therefore, the absolute value of the difference of absolute value of fx and absolute value of fc is smaller than equal to the absolute value of the difference between fx and fc. Now, we have a very, very important estimate which gonna allow us to verify the definition for continuity. The definition for continuity is given in terms of an epsilon delta statement. So we repeat it here. Given epsilon greater than 0, let delta be such that for x minus c smaller than delta in absolute value, then fx minus fc is smaller than epsilon. So this is justified by the definition of the limit equation which we obtained from the continuity of the function f. However, by the estimate star above, we have that the absolute value of the difference of absolute values is smaller than equal to the absolute value of the difference of the function evaluated at x and c, and by the choice of delta, this is smaller than equal to epsilon. So the definition of the limit of absolute value of f of x equal to absolute value of f of c is verified, and therefore the limit of the absolute value of f of x equal to f of c when x approaching c. So in summary, what we did is as follows. We first use the assumption f continuous at c to obtain a limit equation. Using the limit equation, we construct epsilon and delta neighborhoods. Then, using the triangle inequality, we can relate the estimate about absolute value with estimate of the function. That's why the construction of epsilon delta neighborhoods earlier will verify the definition of continuity for the absolute value function. Another example here is about the square root function. Let the function f of x be non-negative. We let the square root function to be defined in the natural way. Now the conclusion is that if the function f is continuous at c, then the function square root of f is also continuous at c. If the function f is continuous on a subset A, then the function square root of f is also continuous on the subset A. The proof is given in the text, and we're going to skip it here. Next, we're going to discuss composition of function. So here, the situation is follow. We have a function f from the set A to a set B, and then we have another function g from the set B to a set of all real numbers. Then the composition function G composed with F evaluated at X is given as follows. This is exactly equal to G evaluated at F of X. So the composition is visualized by this diagram above. So the composition function G composed with F is a function from the set A to the set of real numbers R. This is really composing the effect of two functions F and G in that order. Now the statement, the theorem is that if F is continuous at C and G here is also continuous at point B, which equals F of C, then the composition function G composed with F is continuous at C. So here is an example. Let the function f of x be of any function continuous on a set of real numbers. Let g of x be the absolute of x function. Then you can show that this function g of x is continuous on the set of real numbers. So remember, this function is just equal to the absolute value of its input. So the continuity of this function is very straightforward. It follows from a triangle inequality. By the theorem above, the composition of G and F will be the absolute value of the function f of x is continuous on the set of real numbers. This gives an alternative proof to the theorem we established earlier.